Hello, in this video we're going to be talking about things that can affect the rate of reaction for enzymes. Let's not waste any of your time, let's get right to it. Now when we're talking about things that affect the rate of reaction, for the most part, we're going to be talking about things that just stop the reaction from occurring. And you may be thinking, well, why would you want to stop the reaction from occurring? But what you want to remember is that these pathways are designed to make a particular product. So what would be a reason why a company or a factory would stop making their product? Well, the answer is obvious. They've got enough. Okay, they don't want to make more than what they need and waste materials. And the cells and the enzymes work in the same manner. If we have broken apart some sugars and we've got enough energy to get everything done for now, then we're going to stop breaking down sugars. Now the trick is that the enzymes themselves don't analyze the situation and say, all right, it's time to take a break, we've been working all day, we're done here. There has to be some kind of feedback or some sort of process that stops the work from work, because these are just workers, they're just plow horses. Man, they just keep going and going and going. So there are things called inhibitors, and that's typically a substance that binds to the enzyme and changes its shape to where the substrate doesn't fit anymore, or in some cases, you can see in the diagram, it blocks the active site, okay, to stop the process. And then once it's time to start working again, the inhibitor gets the message that, okay, I need to get out of the way so the enzyme can get back to work. A competitive inhibitor, as you can see, simply blocks the active site. In other words, it competes with that spot with the substrate. Non-competitive is just going to attach the enzyme somewhere and alter its shape, so therefore it doesn't fit. And an uncompetitive inhibitor is pretty similar to a competitive. It just is a little different. But non-competitive, competitive, that's the two we're going to deal with the most. Competitive physically blocks the active site. Non-competitive attaches the enzyme and changes the shape to where the substrate is no longer fits. Alright, so continuing looking at inhibitors and their examples. You can see that on the far left of the diagram beside me, there's a substrate, there's an active site, there's an enzyme, and the inhibitor has physically attached to the active site, blocking the substrate from being able to. Again, that's a competitive inhibition, but it's an inhibitor. The second picture on the far right, that's a non-competitive, and we bring in a couple new terms. Allosteric site, I shouldn't say couple, it's going to lead into allosteric inhibitors, but an allosteric inhibitor is one that is a non-competitive, for one, and it bonds to the place on the opposite side of the enzyme, and when it does that, it changes the shape of the enzyme, and then the substrate will not fit. So both serve a purpose. One is direct, one is passive aggressive behavior, but the competitive inhibitor blocks physically the active site. The non-competitive inhibitor attaches to the allosteric site, making it an allosteric inhibitor, which simply just changes the shape of the enzyme so the substrate can no longer bond with it, or I should say attach with it. Now, when we're thinking allosteric inhibitors, okay, we want to always remember that they're non-competitive. Okay, they are attaching to the allosteric site, and all the diagrams and pictures, it's always on the back side, the opposite side. But simply what it does, it modifies the shape of the enzyme to where the substrate can no longer match. So the inhibitor comes along and binds, okay, and in on the left-hand side of that diagram beside me, and the substrate can no longer fit. You can also have the other direction. If you remember, we talked about a coenzyme, a little converter that allows the enzyme to work on a different molecule. Well, an allosteric activator does something very similar to that. Okay, an allosteric activator will bond to the allosteric, or attach to the allosteric site, and that changes, okay, the shape of the enzyme so it can work on a different molecule. So an allosteric activator is kind of similar to a coenzyme, to where it modifies the shape and allows a different enzyme to be worked on. Okay, so here's another look at this allosteric idea. The allosteric site, again, is on that back side. Okay, the picture on the left is a before, the picture on the right is the after, but it can also go in the opposite direction. So if I put an allosteric activator in that site, it changes the shape to where the substrate can fit. If I put an allosteric inhibitor there, then the enzyme changes shape and the substrate does not fit, which you can see there. Alright, this is half of a picture that we've already seen, but again, we want to talk about these inhibitors on the allosteric site, and of course the allosteric activators. So but the names should always guide you into what's happening. If you see the word inhibitor, that should tell you that they're stopping or blocking the enzyme from working, and an activator would be allowing it to work. Now, one of the things that we're going to be looking at in Chapter 7 is this exact diagram, or one just like it. And this is the breakdown of glucose, the initial breakdown of glucose in a process called glycolysis. Now, enzymes, we want to remind you that they're connected to biological, biochemical, biological, metabolic pathways, whether they're breaking down or building. Okay, but in the idea of what you're going to see in the future, the green writing in this diagram beside me here, those are the enzymes names that are doing whatever is being done to that molecule. So you can see that glucose, an enzyme comes in, and the glucose would attach to the active site, okay, and the work would be done. And now you've got glucose 6, which means it's got 6 carbons, and you got a phosphate. So you can see what was done is that the ATP molecule came in and it lost a phosphate. So it was oxidized, and then the glucose molecule was reduced. Okay, but an enzyme is the one that took that phosphate and added it to the glucose molecule to give it that glucose 6-phosphate name. Then in the next section, the next green word, and these are big long words and difficult to pronounce. It comes in, and again an ATP molecule comes in and it loses a phosphate, and the enzyme there adds it to the glucose molecule. Okay, and then another enzyme will come in, and then you can see it breaks apart. You've got a 6-carbon molecule, so it breaks into 2 3-carbon molecules, which is what those 3 stands for in the glyceride. So this is just an example of these pathways and how the enzyme 1 will come in and do a job, next enzyme will come in and do a job, and they've got specific jobs. Okay, but they're going to bond to the active site, and then we're done. That's a new product that will release. So just a reminder that these are pathways, and the first enzyme will do its job and pass along to the second enzyme, and the third enzyme, on and on until all the work is done. Okay, here's another example of this. You've got the initial substrate. It attaches to the first enzyme and then gets converted to the gold triangle. It attaches to the second enzyme and now becomes the red square. It attaches to the third enzyme, now it becomes the green oval, and then so on until you end up with the 6-sided hexagon after the 4th enzyme. So it's just a reminder, these are pathways. This isn't one event, multiple events going to get it to where it needs to be. Alright, so just one more look. I mentioned this earlier, this feedback process of letting you know when things need to be. And again, you can see this pathway here, this enzyme, the substrate, doing all this work through a series of steps. But you can see that part of one way to get this provide this feedback is to when if there's enough of something, then that substrate can then attach, it'd be to the allosteric site. And that lets it know that, hey, we've got plenty. Okay, we can shut her down, and then once the substrate is used up or reduced amount, then that will drop off and we'll get started again on the production. That's feedback inhibition for the enzyme. Well, that is our second look at enzymes and the things that can affect their performance. This is also the end of our Chapter 6 video series. The next time we get together, we're going to be talking about cellular respiration. So we'll see you then.